So let's look at an application of Gauss's, or rather of Ampere's law. So let's imagine we have a cylinder. This is like a wire or cylinder with electric current flowing down it. And so I want to know if this thing is some radius big R, what is the magnetic field here? Okay, so we got two different regimes. We've got the magnetic field. I want to know the magnetic field when R is less than big R, and I want to know the magnetic field when R is bigger than big R. Okay, so in other words, this will be the magnetic field inside the wire, the magnetic field outside the wire. So let's do the outside the wire first. So outside the wire, okay, then it's spherically symmetric, and this might not be a wire, but it might be, like a cylinder of electrical conductor. Now we know the magnetic field is going to be looping around. So the integral of B dot ds is mu naught times I enclosed. Okay, straightforward. This is going to be, the magnetic field is going to be constant, so this is going to just be B times S, and that's going to be mu naught I enclosed. So that's B times 2 pi R equals mu naught I, because the only I that's enclosed is the total I. And so what we come from that is, just a little bit of algebra, is that B equals mu naught I over 2 pi R. Okay, well, that's the magnetic field due to a wire. So it means it's also the magnetic field due to a cylinder. You can think of a cylinder as a really fat wire. Okay, this is not a surprise. In fact, this should be exactly what you expected to occur. Now let's zoom in here. So this is R. We got current flowing through here. But I want to know what's the magnetic field at some distance R where R is less than big R. So we look at it and say, well, gosh, in electrostatics, we know that all the charge is going to be near the surface of the wire. For electrodynamics, because there's an electric field on this wire, there's current all the way through the wire. So what we're interested in is J, the current density. Remember, J is I over area. So in this case, it's I over pi R squared. Now, if there's a magnetic field in here, if I do my integral of B dot ds, then that's going to be equal to mu naught times I enclosed. Okay. Well, what is that going to be? Well, integral B dot ds, assuming the magnetic field is symmetric, then that's going to come out of the integral, and that just gives me B times S. S is going to be 2 pi R. Okay, that's mu naught I enclosed. So all I got to do is find out what is I enclosed. So I've got my little loop right here of radius R inside the cylinder of radius big R. I know I got current through here, so I got current density, J. Well, the current enclosed in that little piece right there, so the enclosed current is going to be J times the area of the small piece. So the enclosed current is going to be J times pi R squared. Well, J was I divided by pi big R squared times pi little r squared. So the pi's cancel, so that means this is I R squared over R squared. Little r squared over big R squared. Now, that means B times 2 pi R is going to be equal to mu naught times I little r squared over big R squared. So that R cancels that R. And so the magnetic field is going to be mu naught IR divided by 2 pi big R squared. Okay. Now, mu naught is a constant, 2 is a constant, pi is constant, big R is constant because that's the radius of the cylinder right there. So that's constant. And so the only thing that changes is little r. So as I go out, what's going to happen is that the farther out that I go, then the more this changes, okay, the bigger the little r is going to be. So when I'm right in the center of this thing, I've got just as much current on all sides, so little r is 0, so it's perfectly sensible. At the center, then the total magnetic field is 0. And as I get bigger, the magnetic field grows linearly until little r equals big R. When little r equals big R, then the magnetic field is going to be mu naught I over 2 pi r. Now, as r gets bigger, then the big R in there becomes little r in the equation and drops off. And so what happens is, if I made a graph of magnetic field versus r, then if that's big R, it grows linearly. It grows linearly until it reaches that value, and then it drops off as 1 over r. Okay, so that's kind of what the magnetic field would look like if you were to graph it.